So we're going to look at trigonometric functions of positive and negative angles and how they relate to each other. So we're going to do a little picture to start this out, but first I want you to cross out and just write below each of these. I decided that I want this, and maybe you'll be watching this in the future. We're going to already fix this. We're going to start with the negative angles to think about how they relate. So our goal here is to see how the sine of negative theta, the sine of a negative angle, relates to the sine of a positive angle. We're going to draw an acute angle theta in standard position. So we're just going to draw some sort of acute angle theta in standard position. And then we're going to draw, and then we see this angle, if it's acute in standard position, must be in quadrant 1. And then we're going to draw the same acute angle in standard position but make it negative. So we can see if that angle is acute, right? It must be in quadrant 4. We're going to draw a reference triangle for each of the angles. So there's a reference triangle for each one. We're going to use the sines of each side of the triangle to determine the relationships between each of the 3 basic trig functions for theta and negative theta. So if I first off look at sine would be y over the hypotenuse. So I didn't necessarily say to put this in unit circles, so we're just going to write each term. Over here, this is a negative value, and we know the hypotenuse is always positive. So the idea of what's going on here with sine is we see they have the same numbers, right? The y value would be the same because the angles are symmetric. The hypotenuse would be the same the way I drew it, right? So that means that the sine of the negative angle is the same as the sine of the positive angle, but I would have to make that negative to match up with the negative that's on there. So now we're going to move over to cosine and see what happens for these two. So I'm going to erase the y because I don't need it. So here, we see that they have the same shared positive x sine. So if I did the cosine of the positive angle, I'd get x over h. And if I did the cosine of the negative angle, I'd also get x over h. So that means for cosine, the cosine of the negative angle equals the same exact thing as the cosine of the positive angle, because quadrants 1 and 4 basically give us the same values. Tangent, I need to get rid of the 2 hypotenuses and go back to labeling the y and the negative y. So we see for the negative angle, I have negative y over x. And for the positive angle, I have positive y over x. So same as sine for tangent, the tangent of a negative angle is the same as the negative tangent of the positive angle. So we're going to see that this works, and this isn't the main point, but if we did an obtuse angle, it would work too. So we're going to draw another angle, and this time we're going to draw an obtuse angle in standard position and the same negative obtuse angle in standard position. So when I'm in quadrants 2 and 3 now, which is where my angles are, so the positive one has to be in quadrant 2, and the negative one is in quadrant 3. If I drew my triangles, and these do not look quite as symmetric, you can imagine that they're the same angle. I think I can do this. Just kind of this way home. So let's set this one. We can see again, hypotenuses are always positive. The y's have opposite signs, but the x is shared. They're both negative, but they match. So we would get those same relationships where the sine would be the opposite positive or negative sign. Same with tangent because of that y negative y. The cosine would end up giving us the same positive or negative sign, whether we were at the positive angle or at the negative angle. So for these problems, this is a suggestion. So if you have a nice, small, acute negative angle, you can use these identities to figure out the problem without finding a coterminal angle. If you have a large negative angle, probably easier to think about the coterminal angle anyway. So, for example, if I have the cosine of negative 60, we know that that's the same thing as doing the cosine of the positive 60 from this identity. So I could just say, oh, those two are actually the same, and the cosine of 60 is 1/2. If I'm doing sine with an acute negative angle, that's the same as the sine of 30, but we need it to be negative based on this identity. So this is going to make sine of 30 is 1/2, so this is negative 1/2. Tangent of pi over 4, so tangent, I do need to change the sign, is equal to the negative tangent of positive pi over 4, which is 1, so this is negative 1. Cosine, we keep our sign the same. Cosine of pi over 6 is radical 3 over 2, so that's using my middle identity, saying the cosine of negative theta is equal to the cosine of theta. And then we have a couple more down here. So the tangent of negative pi over 3 equals the negative tangent of pi over 3, and the tangent of pi over 3 is negative square root of 3. And the last one, sine. The sine of a negative angle equals the negative sine of a positive angle. So I get negative square root of 2 over 2 for that. Okay, so looking at the next page, we're going to wrap all this up with a little chart. Okay, so how is the unit circle helpful? We've been using it in lots of different lessons. First off, it allows us to work with trigonometric functions without using a triangle. So you started to see, especially for those flat, what we would call flat triangles, we could just use the point, and that's because the hypotenuse is always 1. All we need is a point on the unit circle xy. Another reason for the unit circle, this allows us to extend the trigonometric functions to any angle. So we were doing obtuse angles, even bigger angles, right? Angles bigger than 360, angles smaller than 0, right? Things that couldn't exist in a triangle, or a right triangle especially, right? Well, we can work with these functions for any values of angles. The x point on the unit circle is always the same as the cosine of the angle, and the y value is always equal to the sine of the angle. So from a point, I think I just 2 values. It also allows us to find the trigonometric values of the quadrantal angles, which we kind of talked about in the first part, where we can't even draw a triangle. It gives us the blank, showing a relationship between the sine and the cosine of any angle, as well as many other identities. So this, we're talking about the Pythagorean identity. Our sine squared theta plus cosine squared theta equals 1. And that whole part of trigonometry with identities, we do a tiny little bit of an algebra too, but there's a whole lot more out there that all comes from the unit circle. And then moving into our next unit, which is our second trig unit, it's going to be the basics for creating the graphs of sine and cosine.